Hello, everyone. Today I'm going to be talking about the characteristics of the scientific method. So, the first characteristic of science is the use of systematic empirical evidence as the primary type of evidence. So, yes, the kind of evidence that is used to support theories and hypotheses in science is systematic empirical evidence, not the other kinds of evidence we've been talking about this semester. So, not common sense evidence, not evidence from authority, not anecdotes. You might remember that we talked about personal empirical evidence, relying on one's senses to gather evidence or gaining information through one's observations. This is similar to the technique that science relies on, but there's a little bit more to systematic empirical evidence. So, these are the characteristics of systematic empirical evidence. The first is using accepted research methods and equipment for gathering data to avoid the biases with perception and memory that can occur when we rely on personal empirical evidence. So we talked about the main research methods that are used in psychology. Systematic empirical evidence would involve the use of one of these methods to collect observations. Similarly, in psychology, we also use computers, response boxes, brain imaging devices to collect data. On the other hand, personal empirical evidence will just involve using one's senses to collect information. Systematic empirical evidence also relies on analyzing data using statistical procedures, again, to avoid errors and biases that we talked about with personal empirical evidence. So, does it look like there's a relationship between these two variables in this chart? Or what about in this graph up here? It might look like there's a relationship in the bottom example between arthritis pain and days when it rains, or in the top example between arthritis pain and days when there's high pressure. But in fact, in those two examples, there is no relationship between those variables. So in systematic empiricism, we're going to use statistical methods for determining if there's a relationship or difference between our variables, like the kind you would talk about in Psych 301. The third characteristic of systematic empirical evidence is using control groups, double-blind procedures, etc., to rule out alternative explanations. So think of how we might study the effectiveness of using magnets to treat headaches using systematic empirical evidence versus personal empirical evidence. Using personal empirical evidence, you might get 10 friends put magnets on their head and then have them tell you whether they feel better. If 60% of your friends did feel better, can you really conclude that the magnets were effective at treating their headaches? Well, no, because of things like the placebo effect, spontaneous remission, etc., that we've been talking about this semester. Now consider how we would use systematic empirical evidence. We might get 20 people and have them all put magnets on their head. 10 would be assigned to an experimental group where they would get a real magnet, and 10 would be assigned to a placebo or to a control group where the magnet would be demagnetized. So the magnet should not be having any effect on the body at all. And then we would use a double-blind procedure, so neither the subject nor the researcher would know which condition a particular participant is in. We'd also make sure to treat the groups the same. They would get the same food to eat. They would perform the same activities. We would make sure that there are any confounds in our study. And then we would find out how many people in each group showed improvement, and we would use statistics to see if there's actually a difference. Now, if we find a difference, we would be able to conclude that magnets are effective at curing headaches, but only because we used systematic empirical evidence to rule out all these other explanations. And then the last characteristic of systematic empirical evidence is that observations of nature are structured to test theories, not to record every possible observation. Observation is fine and necessary, but unstructured observations of the world will not lead to scientific knowledge, right? If you write down every observation of the world you make from the time you get up in the morning until the time you go to sleep, you'll have a great number of facts, but you will not have a greater understanding of the world. Instead, studies are set up in such a way to test two competing theories or explanations. One ends up being supported and maintained, while the other is not supported and is rejected. For instance, there's a horse in the early 20th century named Clever Hans who could apparently solve math problems. The horse's trainer would ask Hans questions like, what is 5 plus 3 or what is 2 times 7? And then Hans would stomp his hoof 8 or 14 times to answer the question. A man named Oscar Funkst was hired to test two competing claims, that Hans could actually do math, or that Hans couldn't do math and there was another explanation. The key point for us is that Oscar didn't just observe the horse under random situations. Instead, he set up some very specific conditions to test Hans. In one condition, he isolated Hans and the questioner from spectators so no cues could come from the audience. He then used questioners other than the horse's trainer, and he also varied whether the horse could see the questioner and whether the questioner knew the answer to the question. What Oscar found is that Hans could get the answer correct even if the trainer didn't ask the questions, ruling out the possibility of fraud. However, the horse got the answer right only when the questioner knew the answer to the question and when the horse could see the questioner. This suggests that the horse was responding to subtle, unintentional cues from the questioner. Specifically, Oscar found that as the horse's taps approached the right answer, the questioner's posture and facial expressions became more tense. Then, when the horse made the final correct tap, the questioner relaxed, providing a cue for the horse to stop tapping. So it was through use of systematic observations, rather than just gathering huge amounts of information, that Oscar ruled out the incorrect hypothesis that Hans could actually perform math, and arrived at the correct one, that Hans was an astute reader of human nonverbal behavior. Now note that these are the sorts of things that a scientist goes through to make sure their results are valid. Right? Why did you build a death ray? To take over the world! No, I mean, what mad hypothesis are you testing? Are you just making mad observations? Look, buddy, I'm just trying to take over the world, that's all. You're at least going to leave some of the world as a mad control group, right? Sad truth, most mad scientists are actually just mad engineers. Okay. So our second characteristic of science is that science is a public endeavor. And by this I mean that the results are subject to review by the scientific community before being accepted. So by public, I don't mean that the results of scientific studies are posted on notice boards, but rather that the scientific community engages in the scrutiny and analysis of an idea before it's accepted. In other words, facts aren't accepted until they have been verified by the scientific community. The authoritative statements of one scientist aren't sufficient for declaring knowledge. So again, science doesn't rely on evidence from authority. Results are reviewed by the scientific community in two important ways. The first way is through replication, which is the repeating of a study, either an exact duplication or with a slight modification, to ensure the original study is free from errors. In other words, for a result to be accepted by the scientific community, other people besides the original finder must be able to generate that finding. This process minimizes the chance that the results were based on a coincidence, a mistake, or even bias or fraud, right? A fluke or intentional faking of the results might occur in a single study, but it is less likely that the same pattern would be found in multiple studies, especially in ones conducted by different researchers, if they weren't real. So yeah, if the results can be replicated, that's a good indicator that the results are real. The other way that science is a public endeavor is through the use of peer review, which is the submission of an article to be critiqued by several scientists in that area before it can be published in a journal. So not every study gets published in a journal. Some have methodological flaws that make interpreting the results impossible, some don't add any new knowledge to the field, etc. But others are good studies that will advance the knowledge in an area, and so they can potentially be published in a journal. But before an article is published in a journal, several reviewers look over the article and they try to pick it apart. They look for any flaws or methodological issues, anything they can find to discredit the study. They then present their analysis to the editor of the journal, who decides whether the article should be revised and then published if the criticisms aren't too serious, or if the article is flawed beyond fixing, in which case the article doesn't get published. Now, sometimes mistakes are missed, and not every journal is peer-reviewed, which is definitely something you want to look for when evaluating the quality of a study. But this method reduces the likelihood of flawed, bad research studies getting published. So yeah, I think protesters would get better outcomes if they asked for this. What do we want? Evidence-based change. When do we want it? After peer review. Okay. Anyway, as a result of replication and peer review, science is self-correcting. What I mean by this is that conclusions are changed if more or better evidence is found that supports a competing theory. So in science, we always draw the best conclusion we can based on the current evidence. However, new evidence frequently comes along. Science is unique in that currently accepted theories are readily changed when new evidence comes along if they dispute the accepted theory. So while the currently accepted theories are not necessarily true or proven, they are better and more accurate than the ones from a couple years ago. I like comparing science to car seats, right? Each year, a new and presumably better model of car seat comes out, that's always safer than the previous year's model. So while no model is ever perfect, the newest model is always safer than the previous one. Accordingly, while our understanding of any topic in science, such as the workings of the brain, will never be complete, we have a better understanding of the world nowadays than we did 10 years ago, and we'll have an even better understanding of the world 10 years from now. The last characteristic of science is the use of testable and falsifiable theories. By testable, I just mean that it must be possible to examine the theory using systematic empirical evidence. So yeah, because science uses systematic empirical evidence to evaluate claims, only claims that can be tested using systematic empirical evidence are open to scientific investigation. For instance, what is the meaning of life is not a question that can be answered using empirical evidence, and so it is not a question that scientists can directly answer. But we can answer questions related to it, such as what variables make people happy. And finally, falsifiable means that there must be possible outcomes or results that would show that a theory is wrong. First, let's consider an example of non-falsifiable thinking. In 1793, an epidemic of yellow fever hit Philadelphia. One of the doctors in the city at the time was Benjamin Rush, who was one of the signers of the Declaration of Independence. He believed that yellow fever is best cured by bloodletting, which is the removal of blood from the body, for instance by using leeches. At the time, there were many critics of this method, though, who thought bloodletting wasn't effective. But Rush was very much in support of this method. So how did he test his theory that bloodletting was effective? Well, this was the logic he used. If someone improved after bloodletting, this result showed that the treatment was effective, okay? But if someone died after bloodletting, this result showed that the patient was too ill for any treatment to cure him or her. So no matter what happened, whether the patient lived or died, Rush's theory that bloodletting was effective was supported, according to him. If the patient lived, this showed that bloodletting worked. If the patient died, this showed that the patient was so far beyond help that nothing would have worked. So this theory that yellow fever is best cured through bloodletting is non-falsifiable. No matter the outcome, the theory was supported. So just to clarify then, a falsifiable theory is one that makes predictions that can turn out to be wrong. The theory of gravity, that objects are attracted to other objects with mass, is a falsifiable theory because it makes predictions that can turn out to be wrong. For instance, if objects on Earth flew up into space on their own, that would go against the theory. But of course they don't, which is why we accept the theory of gravity as true. So again, falsifiable theories are useful in science because they make predictions that can turn out to be wrong. Then, those theories that make good or accurate predictions are generally accepted. However, non-falsifiable theories make predictions that must always be true and are thus not useful to science. Here's one more example. Freud says that all men have latent homosexual tendencies. If you are male and have no homosexual urges, then you are repressing them. If this claim irritates you, your irritation is evidence of your underlying homosexual urges. If you're getting confused, that's evidence that your repressed homosexual tendencies are interfering with your brain. You can't win. There's no test to show that Freud's theory is wrong. And so Freud's theory is unfalsifiable. No matter the outcome, the theory is supported. The last thing I just wanted to show you on this slide was something I thought was interesting, a rough guide to spotting bad science. So these are things to be mindful of when reading about and interpreting studies. I won't go into any narration about these, but I encourage you just to flip through the PowerPoint and to look through them on your own. You'll probably notice that many of these we've talked about already this semester, although we might have called them something slightly different.